Okay, so this lesson's about our next unit on the half adder. So let me just explain a little bit about the half adder. Timeout. He wants me to do a timeout. I just started recording something called the half adder. And the whole point of this is to develop a combinational circuit using logic gates that allows us to add binary numbers together. So this is called the half adder. Oh, you guys are not seeing the same thing that I'm seeing. I'm sorry. Okay, I just realized something. Okay, so the half adder. We're going to be doing a circuit. We want to come up with some kind of a circuit here where this looks familiar, right? Two inputs, A and B. We want to be able to add A and B together. That's what the half adder is going to be doing. So we want 0, 0 to give us 0. We want 0, 1 to give us 1. But we want 1, 1 to give us, what's 1 plus 1 in binary? And it's represented as 1, 0, right? So we're going to be, so here's, we're going to do it, it's going to be a 2-digit thing, and it's going to be like this. Here's the output. So we want to come up with a circuit that does that. This is going to be the carry, and this is going to be the single-digit sum. And I'm going to represent that by sigma. So what does the sigma column look like to you? Which basic gate? Any ideas? It's the XOR gate, right? C out and sigma. So we can represent the sigma column by using an XOR gate. And how can we come up with C out using, so we're trying to emulate this or use logic gates to do this. So we, you've got the AND gate, the OR gate. We used XOR already. We can use another gate down here on A and B. And the question is, which gate is it that will give us the C out column? So we want the C out column. So finally, we're seeing some kind of a application to the basic logic gates. So if we AND these two together, let's take a look. ANDing them, this is just the AND, right? C out is AND. So everyone should be able to see that C out is just a basic AND gate. So that's C out. So this is the half adder. That's it. That's the half adder. There's nothing more complicated about it. Any questions about that? So now what we're going to do is we're going to take that circuit, we're going to build on it, and we're going to allow it to accept 3 inputs. So that's the half adder. I'm going to take that away and go to, so let's make a circuit that accepts 3 inputs. So 3 inputs. So we're going to just represent the half adder with this box, and we're going to say HA, ha. So that's the half adder. So here is what we had on the last slide. We had sigma, and over here we're just, instead of C out, we're going to call that W. And we're going to have another half adder over here. So this, what we had on this past slide, is now in the square. That's the half adder. So if I just, that's the half adder, okay? And we showed the truth table. So we're going to have a third thing here. So let's think about this. We've got, guys, are you seriously playing a video game while I'm doing this? BJ? Oh, I should tell you guys there is going to be an evaluation on Thursday on this on D2L. So we're going to have a D2L test on this, quiz on this on Thursday. It's going to be a small one, but nonetheless, I don't want to waste your time the next 4 days. I want to show you something related to computer engineering that's valuable, so this is what we're doing. Okay, so let's just, before we go any further, I just want to show you what we're doing here. We're trying to add up. So 3 inputs, that would allow us to add three digits together. So then we could add something like, for example, 110 plus 010. We could add this up. And we would want the half adder to give us a value like that, 100, for example. So we would have A, B, and C. Is that right? No, that's not right. I'm sorry. We're adding 3 things together, and it's going to look like this. Let me just go back. A half adder with 3 inputs would look like this. So we want to be able to add 3 things together, 3 single digits together. That's what it is. So we want to be able to do this sort of stuff. Whoops. I'll do all the combinations just to show you what it looks like. So 0, 1, 1, 1, 0. And here's the other combinations. We're already halfway done. 1. So I'll put 2 digits here because we are going to get so this is going to be represented by sigma and C out again. Sigma and C out. And then 0, 1, 1, 0. And then finally the last 2 combinations. There's one that is a bit, the last one's different, isn't it? Because we are going to end up with 1, 1. So in all the cases, we're going to be getting 0 or 0, 1, except for in the very last one. So here's A, here's B, and here's C, all right? So we already did the 2, adding 2 digits together, single digits, but what if we wanted to add 3 single digits? And that's where this circuit comes in. So we're going to have to carry again, and that's where this W is the preliminary carry. So here's C is going to the second half adder. We're going to have a sigma here, and then this W comes down, and we want to AND it. We want to AND this together here. So this is C out. So used to writing T. That's C out. So, okay, so why are we doing this? With the carries, we're adding the 2 carries together to get C out. So let's construct a truth table for everything in this circuit here and see that it actually gives us what we need. This is going to be a bit challenging because you can only see one thing at a time. So if I put that up there, I'm going to say construct a truth table for the circuit above, or the one that we just did. So we have, if we look at this circuit that we did, even if you don't, I don't expect you to understand everything right now, and that's why we're doing the truth table, so you do understand it. I'm just going to check back on Teams to make sure that everyone's okay here. On Teams, you're able to see my camera, everything's good. Okay. The camera looks a bit different on Teams. If you're on Teams, are you able to see my whole page and everything that I'm writing? Yeah. Oh, and everything was fine the whole time? Okay. That's weird. The preview in Teams looks different. Okay. All right, we're good. So, yeah. Okay, so we want to have A, B, and C as our inputs in our truth table. So I'm going to do A, B, and C. Let me just back up a minute for those of you that might be confused. We started off with this circuit. It's a half adder, and what it does is it allows us to take two single digits that are binary and construct a circuit that performs addition. Okay, so it performs addition. Remember, we're talking about flashing lights here. If we were in the physical class in a regular school year, you'd be working with these little devices that, well, when A is 0, that means that the switch is flipped off. When B is 0, the switch is flipped off. So this second one here, it's when A is off and B is 1. B is on. So that means that there is current flowing through B. So remember, we're trying to develop the basic building block inside of a computer that allows us to add two bits together. That's what we're doing. And that's what we did with the half adder. But because of the carry out, where does that carry out go? Well, it's going to go, so here's the half adder. It's represented by the box here. It's represented by W. And this whole big circuit, I'm claiming, is necessary for adding three bits together. So we're adding 3 bits. Yeah, the carry goes into the C out along with the carry from the other half adder. So this adds 3 bits together. Sorry, I can barely hear you. Let me fix this. Because I'm using a laptop. And how do I make it louder? I think that's as loud as it goes. From where? Okay, hold on. I don't have it turned on. I have my... I have to get my volume fixed here. I think what I'm going to do is go on Teams on this computer also. Yeah, just hold off for a minute. I'm going to make sure I can hear everybody. This is such a complex setup that I have right here. It's about to get more complex. I'm only going to be using this one for the audio. So if I join this, so I'm going to be there. Now I can hear myself. Okay, go ahead. I can hear you now.
Is like the backwards 3 symbol, is that like that's just an output, like that just represents like the variable?
Okay, so sigma represents sum. It's okay. Sigma, that's the sigma symbol. And have you guys seen that before in math class? No, you've never seen it? Yeah, it is they do use it with fraternities. So the sigma symbol represents summation. Wherever you see it, it always represents summation. If you ever study computer science at university or maybe college, I don't know, and because I've never been to college, but or what else? Computer engineering, or math. If you do any math course in grade 12, you'll definitely see that if you do a U-level math course. So that's the sigma. It's the same as the fraternity symbol that you see, and it means summation. So sigma, let me show you that. Sigma means summation. It's just a variable, okay? So it's just like A or B. We just happen to be using sigma, and that's just universally used. So don't worry about that so much. It's just a symbol. But going on, we want to construct a truth table from this. So A, B, and C are our inputs. You can see that sigma, there's 2 sigmas here. I'm going to make this one sigma 1. Okay, so just make that sigma 1. Summation 1. That one's going to be summation. So let's start off with those 2. So we're going to have sigma 1 here, and then sigma. Now, because we have 3 inputs, we can have a possibility of how many outputs? How many rows should we have? 8, right? I turned my volume down because it was making all kinds of echo. But 0, 0, 0, 0, 0, 1, 0, 1, 0. Okay. As I'm marking, yeah. So you have to do it in this order. If you miss one of them, then it's a problem. So we have all of them there. Looking back at our thing here with the half adder, let's go to the first one. The first one, and you can sigma 1 is this one right here. So it's the same as that column. So it's basically just XOR, right? Sigma is just XOR, as you can see from our very first half adder. So sigma 1 is just XOR. XORed with what? What's A, B, or B and C? It's A and B. So we're going to do XOR with A and B to get the value of that. So we get 0, 0, 1, 1, 1, 1, 0, 0. And the next column, sigma, is the summation from this half adder. And where are those coming from? That's from sigma 1. It's XOR of sigma 1 and C. So we're going to do the XOR of sigma 1 and C. So these two columns here. Pardon? Can you see it on Teams? Oh my gosh. Are you serious? You can't see the screen on Teams? Could you see it before? And then all of a sudden it went away? Why did it all of a sudden go away? Are you sure? Because I can see it. Josh Pafundi. Is it because he's presenting? Oh. So you guys can't switch back to my screen? Yeah? Okay. Where am I? Where is my name? Oh, okay, I see. Okay. Spotlight me. Is that better? Okay, everyone can see me now. It's important that you saw what I was doing. Why don't I just explain what I just finished doing just at one more time, because I think some of you were not. This video is going to be very long, and I'm probably not. I can post it, but there's a lot of stops and starts. So we want to construct a truth table for this circuit to see if it actually adds up three bits together. Because I'm claiming that this is what it does, and we're just kind of proving that. So we have, for this first half adder, we want to determine what sigma 1 is. There's two inputs for each half adder, A and B, or 2 anyway, and then there's 2 outputs. One of them is the summation for the ones place, which is sigma, in this case sigma 1. And the other one, we had C out, which I'm representing by W. I'm just calling it W, because we're going to be using C out at the very end there. So the sigma column is the ones place. It's represented by an XOR. So if we go back here, sigma 1 is XOR of A and B. So we're going to do an XOR between A and B, and that's what we did in that column. Sigma is the XOR of sigma 1 and C. So we're going to do an XOR with sigma 1 and C. So these 2 columns. So let's do an XOR. So the only time we get 1 is if exactly one input is 1. Okay, so we're getting there. The other columns we want are W and X, and then finally C out. So we're almost there. W and X. And remember, those ones were just ands. So if we look back at our original half adder, because that's what our box represents, we can see that our other output for the half adder, which is C out here, it's W in this one, is the AND gate of our two inputs. So what are our two inputs, A and B? So we're just going to do A ANDed with B for W. So A ANDed with B. The only time we'll get a 1 is at the very end, right? The 2 at the end. The 2 at the end. And then X is the AND for, well, X is right here. I didn't even label it on the graph. I'm sorry about that. But they're X. We do need to know what that value is, and I'm representing it by X so that we can get C out here. So X is the AND. We're going to AND sigma 1 and C together. Sigma 1 and C get ANDed together, so we get 0, 1, 1, 1, 1. Oops, I'm sorry. And these should be 0, right? The only time we get a 1 is if both inputs are a 1. So finally, C out. What is C out? It's the OR of, we're going to OR W and X together. We're going to OR W and X together. So we got 0, 0, 0, 1. And these don't really match up. I apologize for that. Let's see if I can fix this up for you. Perhaps I'll use lined paper in the future. I don't know. This is all kind of new to me. And then 1, 0, 1, 1, 1. So let's see if this makes any sense. So if we look at our diagram, we're going to be using sigma and C out. Those are the two columns that we're interested in. Sigma and C out. Sigma represents the ones place. So I'm going to put this beside it and see if it matches up correctly. So we've got A, B, and C. When A, B, and C is 0, 0, 0, the first one, we should get 0 for C out, 0 for sigma. So these two, unfortunately, they're reversed, but we can look at that. 0, 1, 0. 0, 1, 0 is down here. 0, 1, 0 is down here. We should be getting a 1 for sigma and a 0 for C out. So that works out. Let's skip down to here when we have 1, 1, 1. 1, 1, 1, we should get a 1 for sigma and a 1 for C out. And that's good. It looks like this is matching up so far. And you can check any of the, 1 plus 0 plus 1. 1 plus 0 plus 1. There's a 1, 1 here. Is that correct? No, this should be a 1, 0. Why? So why? I just want to go back and take a look at why that one is different for C out. Everything else seems to match up fine. 1, 0, 0. 1, 0, 0 goes to 0, 1. Okay, there's a problem here. I'm going to be coming back to this. Because a 1 here, right? That should be a 1. That should be a 0. Something in the same area. Is everything else okay? 0, 1, 0. This should be. So I'm going to come. Oh, I'm looking at the wrong columns. I'm looking at the wrong columns. It probably is fine. Jeez. Okay. Because we're looking at sigma here. Okay. Start over again. 1, 0, 1 is 1, 0, 1, 0. And remember, C out is first. Okay, that's fine. I think we're good. 0, 1, 0 is 0, 1. Everything matches up fine. You just have to be aware that C out is the tens place, but it happens here. So this is the tens place. This is the ones place. So basically what I did is I showed you this that was already known. You can look this up online. That is a 3-bit half adder. And we just showed that the truth table shows that it's correct. So what we can say is we can say A plus B plus C. And remember, we're actually talking about plus here because we're doing 3-bit adder here is equal to, and if we have two placeholders, this would be C out and this would be sigma. Okay? Those are the two placeholders for that. So what I'd like you to do is wire up the half adder and verify it, and then do the full adder lab that I'm going to have uploaded using a certain chip, and that'll be all online in D2L. So first thing to do, wire up the half adder. And verify that it works. So in order to do that, you need an XOR gate and you need an AND gate and just 2 inputs. And that's something that you can do on Tinkercad. I'm going to switch my screen now. So I'm going to go and use, start casting the video from my screen. Stop sharing my video. I'm going to stop this recording as well.